Here's another example of local linearization. So the key formula for local linearization is this. We're taking a function f of x, and we're saying near x equals a, we can approximate it well by its tangent line. So this is just a quick way to get the tangent line approximation. Local linearization and tangent line approximation mean the same thing. So this is a formula that, of course, you can always look up, but hopefully it makes sense. So this says that f of x, we're thinking about what's going on with f of x near a. So f of a, that's what the function actually is at a. And then we just want to know, how does it change if I go a little bit to the left or to the right? So this term here, x minus a, that tells me how much to the left or the right I'm going. And this is just the slope of the function at a. So it tells me, it converts a run, a move to the left or right, into a rise, a move up or down. All right, so let's do this example. Find the local linearization, i.e. the tangent line approximation, for the natural log at x equals 1. So that means that in this formula here, a equals 1. And the function, that's f of x, or we've got f of x is natural log of x. F of x is natural log of x. So I need to take the derivative. I'm going to need that. So that's f prime of x. And the derivative of natural log is 1 over x. So now I've got all the ingredients to use this formula. So the local linearization says that f of x is approximately f of a, and that's going to be log, well, I'll write this out, log of 1. Plus the derivative at a, the derivative is 1 over x, so that's going to be 1 over 1 times x minus 1. So I'm plugging into this formula using the function f of x is log and a equals 1. And this simplifies right away. Log of 1 is 0. That's nice. 1 over 1 is 1. So this whole thing is x minus 1. So let's think about this geometrically for just a moment. I'll try to draw this over here. Here's x. This is log of x. And remember that the natural log function looks like this. You've got one on your hand, right? So this is the exponential function. That's the log function. Mine doesn't quite go down as far as some people's do, but anyway. So log function is this very negative but then very slow growing sort of function. And this line x minus 1 is the tangent line approximation to the natural log. And here's a more high-tech version of that figure. This is from our friend Wolfram Alpha. So this is log x and x minus 1 from 0.8 to 1.2, and they're almost on top of each other. So the one with a little bit of bend in it, the lower one by my fingers here, that's log x. And then this straight line is the tangent line approximation, which we found is 1 minus x minus 1. So as expected, as we get closer and closer and closer to this point, the point we're doing the approximation around, the tangent line approximation gets better and better. And that's equivalent to saying, right, if we zoom in on a function, closer and closer, the function looks like a line. And so here, sorry it doesn't quite focus this close, the tangent line and the function itself are right on top of each other. They're indistinguishable. So I know that local linearization seems like a sort of silly thing. Why would you want to take a nice curvy function and turn it into a line? But it does come up. It's a very useful thing in science very often. So it's definitely a good thing to know about, and hopefully this example makes it a little bit clearer.